Hello all, welcome back to this online recording sessions in deep learning from data science concepts. Okay, so this is Akhil from VJEC working as an assistant professor. So we are going to see one of the deep learning concept, that is weight initialization and batch normalization in this lecture. Okay, so what is exactly the weight initialization, why we need this weight initialization? Okay, so previously while using ReLU activation function, we have overcome the dying of ReLU activation functions. Okay, so why that? Okay, so why, in order to overcome that problem, we need to have come to a conclusion that we need to have proper weight initializations. Okay, the weights that we are giving as inputs, we need to be initialized properly. Okay, so similarly we have one more topic also, batch normalization, where we will be normalizing the entire data into between the ranged values. Okay, yeah, let us see what is the first initialization technique. Okay, so let me draw this one diagram. Okay, let me draw one diagram. Yeah, so so the information will be passed on like this, right? So the information will be passed on like this. Okay, so nothing but weights. Okay, so our weights, with the help of weights. Okay, weights are nothing but they're carrying some inputs. Okay, they are carrying some information. Okay, so what are the various techniques? Okay, so we'll having W11, so W12. Okay, so W13, so like this we will be having the weights. Okay, so these are inputs, right? So these are weights. Okay, so these are hidden layers. Okay, so F11, F12, F13, okay, F21, F22. Okay, like this we'll be having the architecture. Okay, so here we are observing the weights of the that we are adding in the deep learning architecture. Okay, so this is the zero initialization. Okay, zero initialization. So we are discussing step by step what are the different kinds of weight initialization techniques. So the very first one is zero initialization. Okay, so it is generally not recommended, but it is better to know that it is present in our deep learning concept. Okay, so all the weights are set to zero. Okay, all the weights are set to zero, which leads to symmetric problem where all neurons learn the same features. Okay, so this situation, this initialization may be helpful in some cases. Okay, not in all, may not be in all the cases, but maybe in some cases. Okay, so during any kind of constant initialization also the same issue happens to occur. Okay, so generally if any issue is happening, so the same issue will be occurring it again and again. So generally we don't prefer it, but it is better to know it. There is a zero initialization, so we cannot give any weight to that particular weights also. Okay, they are zero initialized. Next, random initialization. Okay, to overcome shortcoming of the zero or constant initialization. Okay, so instead of giving the very constant weights. Okay, so during loss function and backpropagation, we are observing that the weights are getting modified, right? So the weights are getting modified, then how the weights are getting initialized. Okay, so the other method is random initialization. Okay, so in the random initialization, what is happening? The shortcoming of zero or constant initialization. Okay, so in previously the initialization is zero or it is constant. So random initialization assigns random values except for zeros. Okay, except for zeros. For constant values it will assign some values. Okay, okay, so as weight to neuron paths. Okay, so assigning these values randomly to the weights. Okay, so problems such as overfitting, vanishing gradient problem, exploding gradient problem might occur. Okay, assigning values randomly to the weights. Okay, these problems may be occur due to this random initialization. Okay, like overfitting, vanishing gradient problem. So what we need to do? So weights are initialized randomly using a small normal or uniform distribution. Okay, so subcategories. Okay, subcategories of random initialization. Okay, if you just randomly initialize with some random numbers, we may get these problems, right? So that's why we will break the subcategories. Okay, so one is random normal, the other one is random uniform. Okay, so there are two kinds in random initializations. The first one is in random normal, the weights are initialized from values in normal distribution. Okay, so in normal distribution form we will be initializing the weights. So in the other form of random initialization, we also have random uniform. So in this, what the weights are initialized from values in a uniform distribution. Okay, so here normal distribution, here uniform distribution. Okay, so the distribution is changing here. Okay, next Xavier-Glorat. Okay, Xavier or Glorat initialization for sigmoid or tanh. Okay, so for sigmoid and tanh functions, how do we initialize the weights? Okay, so it is proposed by this author, so that's why we are calling Xavier-Glorat. Okay, it is suitable for sigmoid and tanh activation functions. When you are using them, this weight initialization technique will be helpful in that case. Okay, in order to ensure variance remains stable. Okay, variance remains stable, overfitting. Okay, overfitting remains stable, we can use this. Okay, so this is the formula for that. Okay, for Xavier-Glorat initialization. Okay, so Xavier-Glorat initialization, often termed as Xavier, okay, uniform initialization, which is suitable for layers where activation function is sigmoid. Okay, for sigmoid and tanh, right? Next, He initialization. Okay, He initialization, where it will be used, this initialization technique. Okay, for ReLU and leaky ReLU. Okay, if your activation function is ReLU or leaky ReLU, then we can use this weight initialization. Okay, it is introduced by Kamyang Hing. Okay, designed for ReLU. Okay, so for design, he has designed for ReLU activation function. Okay, so he has given this formula to update the weights every time. Okay, so he is nothing but the weight initialization. Okay, He uniform initialization technique is suitable for layers where ReLU activation function is used. Okay, yeah, conclusion. So what is the conclusion? We have seen Xavier and we have seen He. Okay, so He initialization, random initialization and zero initialization. Okay, few initialization techniques, right? So what do we conclude, okay, from this weight initialization techniques? Okay, so weight initializations are very important concepts in deep learning. Why? Because using the right initialization techniques can affect the accuracy of the deep learning model. Okay, so the exact accuracy of the deep learning model can be depending upon the weight initialization technique. Okay, hence weight initialization techniques to be considered as more important during the weight consideration. Okay, depending upon the activation functions we can consider. Okay, so what are the factors that are responsible, you can see it, and what are the activation functions. Okay, so based upon all these constraints we can select the required weight initialization technique. Okay, next we are going to see batch normalization. Okay, so what is batch normalization? Okay, see, so the values may be the outputs may be varies. Okay, it may be 0, 0.1, 1.2, 1.5, 2.8, 10.6, 100.8. Okay, see, so few are related between 0 to 10. Okay, but few points are over. Okay, so the values are very, very large. Okay, so in that case what we need to do, we need to normalize between 0 to 1 or some between time intervals. Okay, between between two constants. Okay, so we'll be normalizing all the values. Okay, in the form of batches. If we do it, we call it as batch normalization. Okay, yeah, what is batch normalization in context to deep learning? Okay, so we have seen regularization tools. Okay, regularization L1 L2. Some can early stopping, dropout, weight initialization techniques, and batch normalization in CNN. Okay, so what it is exactly batch normalization in all these cases of deep learning concepts of above. Okay, yeah, it is a technique that normalizes the input of each layer to stabilize and speed up the training. Okay, why we are constraining all the inputs that are 1.8, 1.6, 2.5, all that we are rounding off to between two intervals, 0 to 1 or 0 to 1.5. Why we are doing means in order to speed up the training. Okay, it was introduced by Loff and ZD, okay, in 2015. Okay, this batch normalization technique. So okay, it helps us address the internal covariant shifts, making deep neural network easier to train. Okay, so for training easier purpose, okay, for making the network easier to train, this batch normalization technique was designed by Lofi and Zedi. Okay, these two authors designed in 2015. Okay, to make training proper. Okay, in order to avoid fluctuations and shifts, covariant shifts. Okay, so why we use batch normalization? Okay, to stabilize the learning. Okay, we need to stabilize the learning. Okay, internal shifts. Okay, for faster convergence. Okay, to reduce dependence on weight initialization. Okay, so every time we need not depend upon the particular weight initialization technique. So in order to avoid that weight initialization technique, for faster convergence we can use batch normalization. Okay, which allows us to higher learning rates. Okay, regularization effect. Okay, can reduce the need for dropout by adding slight noise during training. Okay, next, improved gradient flow. Okay, for improved gradient flow also we can use batch normalization. Okay, so these are the 4 scenarios why we need to use batch normalization. Okay, okay, what are the steps to be performed? Okay, there are different steps, step by step procedure in order to perform this batch normalization. In step 1, we compute the mean and variance of mini batches. Okay, batches. Okay, the inputs will be in batches, right? Input will be in batches. Okay, so these batches will be finding mean and variance. Okay, we will be finding mean and variance for these batches. Okay, so for mini batch of activations, x1, x2, x, okay, mx1, okay, x2 and so on, xm. Okay, this means ub is the, what is ub and rho square b? So rho square b is the variance, nu b is the mean. Okay, okay, of the mini batch. Okay, of this batches. Okay, next, step 2, after finding mean and variance, we will normalization, we will apply general normalization. Okay, each activation xi is normalized using the computed mean and variance. Okay, using this mean and variance we will normalize individuals. Okay, okay, individual batches. Okay, next, the second step only, normalization process subtracts the mean ub from the each activation and divides the square root. Okay, divides the square root. You can see here, it normalizes the, it subtracts the mean. Okay, this is the mean from individual weight. Okay, individual weight is subtracted from the mean, and then we are adding the, taking the square root of the variance. Okay, variance down here you can see this is the variance. Okay, that the normalized activation functions have 0 mean and unit variance. Okay, so this is the actual formula to be used in order to perform the batch normalization in second step. Okay, in third step we will be scale and shift the normalized activations. Okay, what actually we do here? So okay, we will do xi values are scaled by learnable parameters. Okay, so we'll be considering gamma, beta parameters, some scalable parameters, then we'll be shifting those values to nearer to that parameters. Okay, shifted by another learning parameter beta. Okay, so normalized activation function xi are then scaled by the parameter gamma and shifted by another learnable parameter. Okay, beta. Okay, so different learnable parameters are considered here if you observe. Okay, then the parameters are adjusted. Okay, this parameters helps the model to learn the optimum scale so that it will not do fluctuations. Okay, during normalization. Okay, which helps the okay, so this is what batch normalization in TensorFlow. You can see it here with the help of TensorFlow. How we can do, we have added the batch normalization using tf.keras.layers.batch normalization. Okay, if you use this command in your code, batch normalization can happen using TensorFlow. Okay, so what are the benefits of normalization? Okay, faster convergence, high learning rate, regularization effect, which you have seen previously. Okay, okay, so conclusion. Okay, so what is the conclusion that we can conclude by why we need to apply batch normalization? Okay, okay, we can say batch normalization is a powerful technique for stabilizing the training. Okay, training of deep neural network. Okay, we need to stabilize it. Okay, for that purpose we are applying normalization. Okay, by normalization the inputs of each layer address the issues of vanishing gradient. Okay, each layer will address the vanishing gradient problem. So indirectly we will try to sort out the vanishing gradient problem with the help of separate individual points, okay, individual inputs. Okay, so batch normalization. Okay, in Keras, integrating batch normalization into your model is simple. Okay, if you use Keras instead of TensorFlow, it will be also a better approach in designing the batch normalization. Okay, in order to get a better performance as you explore the depth of the TensorFlow. Okay, so that is what about the batch normalization and weight initialization techniques. I hope this concepts will help us in on deep learning concept while we are designing the architectures and designing the models in deep learning. Okay, so thank you all. So thank you for giving this opportunity once again. Thank you all.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.